All right, a little bit on Earth dimensions. Structure of the Earth, basic structure, four main layers: crust, mantle, outer core, inner core. Crust is top layer, mantle next, also the thickest. Outer core is next, which by the way is liquid, it's molten, and then a solid, dense inner core. And we'll break it down a little further as we go. If you pull over to page 10, you can see that we have the interior of the Earth on page 10. Hand down, we have pressures in millions of atmospheres. You can see as we go deeper, pressure increases as we go deeper, right? Same thing with temperature. As we go deeper into the Earth, temperature increases that way, all right? All right, so shape of the Earth. Basic shape of the Earth is what we call an oblate spheroid. All right, it's spherical, but it's slightly oblate, slightly squished at the poles. And that means that our equatorial circumference, the distance around the equator, is going to be greater than its distance around the poles. That difference is not very much. It's about 40 miles. All right. So if you think about the size of the Earth, that 40 miles is very insignificant. That's why we say the Earth is almost perfectly spherical. Not quite perfectly spherical, but almost perfectly spherical. Pretty close. All right, the two R's. Got to know the difference between rotation and revolution. Rotation is spinning. Right? Spinning on an imaginary axis that runs from pole to pole. Look at the picture. You can see that Earth spins from west to east. Okay, so if I'm down here, I spin from here to here. So if you see how this left side is lit up, that means the sun is over here somewhere on the right. Or excuse me, right side lit up, excuse me. Sun is over here on the right. So anybody sitting on the Earth, as they rotate in, the east side is going to go into the light first, and then on the other side, it's going to go into the dark first. All right? So the sun rises in the east, sets in the west. That's where that comes from. All right? Now, what is our rate of rotation? We already established this from the last one. All right? Counterclockwise, 360 degrees. Takes 24 hours to do that. 15 degrees per hour. That's where our longitude comes from. All right? Okay? That's where our time zones come from. The Earth spins one complete 360-degree rotation in a 24-hour time frame. All right, 15 degrees every hour. All right, how do we know the Earth rotates? We've got a couple of pieces of evidence. All right, the first is a pendulum. It's created by Jean Foucault, a Frenchman, and he showed that if you put a weight on the end of a cable or a chain of some sort and you swing it back and forth, it will continue to move in the same direction over time, but the Earth will spin underneath it. And so to us, because we're standing on the Earth, it appears that the pendulum is going to change direction. Okay? And the second piece is the Coriolis effect. Coriolis effect is the apparent curvature of things, wind, projectiles launched from the Earth, etc. They appear to curve as they move. They don't actually curve. They're flying through a nice straight line. The wind is blowing in a nice straight direction from high pressure to low pressure. It appears to curve because of the Earth's rotation. And how much does it appear to curve? 15 degrees every hour. All right? So we got to take that rotation into account. All right, what are the effects of Earth's rotation? Well, one, night and day. All right? When the sun is directly over your longitude, you have noon. Then as you're rotating, you're going to rotate into darkness first, and then you're going to rotate into light first, so that rotation into dark and out of dark, into light, out of light. That's our sunrise and sunset. And you can tell what time it is at any point on the earth just by looking at where the sun is in relation to your longitude. If the sun is directly over your longitude, that's noon. If the sun is opposite your longitude, that's midnight. And if this is midnight, that's 6 in the morning because we're going counterclockwise. That's noon. That's 6 at night. So again, if I start at 6 a.m., there's 9 a.m. Anywhere, somewhere right in here is 9 a.m. There's noon. Somewhere right in here is 3 p.m. Here's 6 p.m. Somewhere in here is 9 p.m. There's midnight. And then somewhere in here is 3 a.m. So you can figure out time on the earth anywhere just by knowing where your longitude is in relation to the sun. All right, the other R, revolution. This is something orbiting around something else. It's not spinning now. We're not talking about spinning. We're talking about something going around something, like the earth going around the sun or the moon going around the earth. All right, our direction of revolution is the same as our direction of rotation. It's counterclockwise as viewed from above the North Pole. Rate is different. Remember, rate of rotation was 360 degrees over 24 hours, gave us 15 degrees per hour. This is one complete revolution around the sun, 360 degrees, but now it takes 365 days for the Earth to get all the way around the sun. If we take 360, divide by 365, it's about 0.98, 0.99, something like that. And so we round it to about a degree per day. Right? Yeah, it's not exact, but about a degree per day. All right, what are the effects of Earth's revolution? Well, different stars, in this case I've got constellations up here, different things are visible in the night sky at different times of the year. So if we see where the sun is right here, and where the Earth is right here, if I were looking at the sun, which means I'm in my daytime, I can't look through the sun and see these guys over here in the sky. They're there, but the sun is so bright that I can't see them. But when I spin over here to this side and it's nighttime, I can see these guys over here very easily. Okay? When I revolve over to here, now I can see all these guys, but I can't see through the sun to see all these guys, and etc. as I work my way around. So as the Earth goes around the sun, at different times of the year, we can see different things, different constellations, different things in the night sky. They change as we go. All right, here's a little picture of what the path of the sun would look like on any particular day. All right, we had those those 4 key days of the year. We had our first day of winter, our first day of spring or fall, and our first day of summer. Notice in winter, the sun doesn't get very high above the horizon. This is facing south, right? We always look to the south to see the sun. Look to the south to see the sun. North to see Polaris. Okay, North Star, north. Notice on the equinoxes, fall and spring, it's a little bit higher in the sky. And then in summer, it's highest in the sky, up around 70 degrees above the horizon. All right, so let's take a look at our dome of the sky. All right, our imaginary dome. Summer in New York, first day of summer, right? Summer solstice, right around June 21st. Remember, these are approximate numbers. It's not exact all the time, but approximately June 21st. We're going to get about 15 hours of daylight. Our sunrise is going to be north of east, and our sunset is going to be north of west. So our apparent path, the path that the sun is going to take through our sky, in terms of what we see, is going to look kind of like this. All right, the sun rises over here in the northeast, takes a long path through the sky, reaches a peak at about 70 degrees above the horizon at noon, due south, and it sets north of west. And this whole line right here is about 15 hours long. Okay, the sun is high in the sky, and it's out for a long time. Summertime, hot, higher temperatures. Okay. Now, if we look at fall or spring, this path is the same for both. In this instance, we're right around September 21st, 20th to the 23rd, somewhere in there, and right around March 20th to the 22nd, 23rd, somewhere around there. All right? These are our first days of fall and our first days of spring. Here, everywhere on the planet, there's 12 hours of daylight and 12 hours of darkness approximately. All right? Equinox. The word equinox means equal night. So we get 12 and 12. Here, this is where the sun rises due east, and it sets due west 12 hours later, and it rises about halfway up in altitude at noon. So it's going to look something like this. Key thing to look for is what that sunrise and sunset due east and due west. It's 12 hours in our hemisphere and 12 hours in the southern hemisphere. And then our last one is our winter solstice, okay, right around a few days before Christmas. Here, we're only getting about 9 hours of daylight, which means we got about 15 hours of darkness. And you guys know what I'm talking about in the middle of December, January, when you go home from school at 3 and 2 hours later the sun drops down. 5 o'clock, it's pitch black out. All right, so you know what I'm talking about. Here we have our sunrise a little bit south of east. Our sunset is a little bit south of west. And the sun takes a shorter path through the sky. It's not as high in the sky. It looks like this. So because the sun is very low, we don't get very direct rays. A lot of them bounce off. And the fact that it's only in our hemisphere for 9 hours, which means it's in the southern hemisphere for 15, which means that they have opposite seasons of us. All right? When we're having winter, they're having summer. When we're having summer, they're having winter. It's just opposite. But again, low sun, not many hours, colder temperatures. All right, if we put them all together, it kind of looks like this. All right, you can see here we've got our summer path right here. We've got our fall and spring path right here. And we've got our winter path right here. By the way, here's Polaris. Remember I said you look for the noon sun due south, and you look north for Polaris at night, because Polaris is the North Star. All right, so this is our motion. These are our motion of our sun and stars. Remember, the sun is a star, okay? It's just we're so close to it, it's so bright, that's why we have daytime with it. All right, the other stars, they're not that bright because they're far away. All right? The apparent motion of the stars changes when the latitude on Earth changes. This is what Verona looks like. Okay? This is what New York State looks like, 43 degrees north. This is us. All right? This is the path of our sun for winter, spring, fall, and summer. And remember, because the Earth rotates west to east, they appear to move through the sky east to west. That old expression, the sun rises in the east and sets in the west. It's because it's opposite of our rotation. Our east rotates into daylight first, and our east rotates into darkness first. All right, here's another look, but from the opposite side. If I go back for a second, notice here I've got west on the far side, east on the near side, north to the right, and south to the left. But here, I've got the opposite. I've got north to the left and south to the right. So in this instance, we're going to have our sunrise on the opposite side of this diagram, but the picture is identical. It's just reversed. That's all. It's just reversed. You just have to know where your north and south is. The sun is always at noon in the south. Okay? Here's a couple of pictures showing different places. All right, 50, notice 50 degrees north is very similar to where we are. It's a little lower in the sky. The higher in latitude you get, the lower the noon sun becomes. The lower at the equator, notice it's directly overhead almost all three. This is why the equator is hot all the time. We also get 12 hours. Notice 6 a.m. to 6 p.m. we get 12 hours all year long if you lived at the equator. And the sun would be really high in the sky all year round. because the sun is really high all year round. That's why the equator is pretty warm all year round and consistently warm. Right? Down here, this would be if you lived at the North Pole. If you lived at the North Pole, notice your path for June never sets. Notice that the paths of the sun run perpendicular to where Polaris is. Okay? Here's another look. Top left would be 40 degrees, just a little bit south of New York City, right, on the first day of summer. This would be a little bit south of New York City on the first day of summer. Here's a little south of New York City on the first day of the equinox. Rises in the east, sets in the west. Here's December, rise in the east, sets in the west. And here would be the June 21st, 24 hours of daylight. And this is at 80 degrees latitude north. This is approximately almost the North Pole. Notice what happens. The sun is at noon here. At midnight, it's here. So the sun never sets for a period of time. And at 80 degrees north, you're probably looking for 24 hours of daylight for probably 5 months or so, a little over 5 months, and then you would have a small in-between season, and then you're going to have 5-ish months of no sunlight at all. Right? Anything above the Arctic Circle, you're going to have a period of time where you're going to have all daylight or all darkness, depending on the time of the year. Here's another view. This is showing the northern hemisphere here. Okay, here's our summer path, which by the way would be their winter path, shorter, see that? Our equinox path is the same as their equinox path. It's just opposite seasons, fall and spring. And then our winter path is their summer path. Okay, so the seasons are just opposite. And where do those numbers come from? 23.5 degree tilt between them. Okay.